Can you do that again? Thank you.
Enjoy.
Do you know how to Dougie? That's just wrong. All right, what do I need to do? Oh my goodness gracious.
Dude, get Dougie so bitchy.
Something wrong with you.
We all knew that.
Okay.
Brandon, can you do the Dougie?
Can you do the stanky leg? Okay. Electric motors. Why don't one of you explain to me how motors work?
Electricity goes in, gets the winds, and comes out.
That's how the current flows, correct? What makes it spin?
Different polarities. Magnetic field created by the electrical current moving through it.
Yep. Ooh, this is fun. All right, so just for a short spiel, you guys should know this already, but I guess we'll review it a little bit. Y. This is represents a Y wound motor.
W-Y-E, right?
Right. So if you think about this, dude, if you're just gonna sit here and watch videos, you might as well go home. If you think about this in terms of current flow, as this current is approaching, let's say this is the motor shaft. Keep your mind out of the gutter. As we're approaching this winding, depending on the polarity of that winding, as we approach this peak, there's a pull happening at this winding, right? And this is a sine wave, so current's going to alternate. It reaches this winding, and then that pull actually starts to become, once it gets to the alternation point, a push. And that's happening simultaneously across all three windings, right? Because it's three phase. So there's that whole push pull thing going on. So as this one's starting to push away from it, this one's starting to pull towards it. And you've all seen how current and magnetism are related, directly related. That's like the most compact explanation of how a motor works that I've ever done. But I guess it helps to do a short review of that first. This PowerPoint is based more on general service of motors and not so much the motor theory and what makes it work, but we're going to get into horsepower and torque and all that good stuff. So okay, electric motors are in use throughout every manufacturing plant, office, and home. This is an older PowerPoint, but I would imagine that these numbers that you're seeing now are more inflated today than they used to be. But just imagine that they consume 64% of all electrical power generated is consumed by motors. And you wouldn't think that because you're not always seeing them. But you would think that it would be like lights, right? Lights and maybe computers, office equipment. But motors are what is actually doing the most work. They draw the most current. So it does make sense that they would consume most of the power generated by power plants. It says about 1 billion motors in service today, consuming over 1 trillion kilowatt hours of energy per year. And I would definitely imagine that those numbers are higher than what you see right now too. And this doesn't matter, but in case you want to know how many zeros are in a billion and a trillion, and then you take a trillion times 1,000 because it's kilowatt hours, that makes a quadrillion. So that's a lot of zeros. So in general, motors are classified either as AC or DC. And there are 3 different types of configurations for the windings for DC motors. So what are they?
The WYD.
No, look at the slide. Look at the slide.
One is definitely series.
And this, we're talking DC.
Oh.
We're talking DC
Shunt-
direct current.
Shunt compound series.
Right. Series, shunt, or compound wound.
My bad.
And you'll hear me along throughout this PowerPoint emphasizing things. Hint, okay? Like I just did. So you got DC motors up here, AC motors down here, which can be classified as 2 different things, single phase or polyphase. Picking up what I'm throwing down? And then what's this little yellow thing in the middle?
Universal.
What do you think that means?
It could be DC or AC.
Correct. Very good. And then amongst all these different single phase and polyphase motors, you have this induction, synchronous, squirrel cage, wound rotor, all this crap. We're not going to get into all that fun stuff as to how these things are made and how they work and how they function. They all work on the same principle of electromagnetism. So you got your DC motor, synchronous motors, and induction motors. Whoa. DC motors are, you can imagine, used in small applications, smaller type motors. Why do you think that is?
Can you repeat the question?
Why do you think DC motors are used in smaller applications?
Because the voltage is smaller, I would say.
That's a yes. That's exactly right. So why wouldn't we use a 20 horse DC motor on a big crane? You'd probably need a shit ton of voltage,
Right.
right? DC motors are very,
Our vending machine, those are 24 volt.
Yeah.
And they're small. So
mhm.
if we have to put them all together, we'd have to like a lot to get a big voltage, correct?
Correct.
Or either that or you have to put a lot of voltage through one motor. When you burn it out faster or something, maybe?
Not necessarily. I mean, if all the parameters are right, if the voltage is correct and the load is correct, then you would theoretically never burn up a huge DC motor. But think about DC motors are really easy to adjust the speed on, right? You're just raising or lowering the voltage.
Right.
For the most part. That's a really easy way to adjust the speed. But when you adjust the speed with a DC motor, and think about a small motor, do you have a small motor? And the first place my mind goes to is, because I have kids, Power Wheels motors.
So I got a motor back there I can bring you.
Sure, go grab it. Little bitty 24 volt motor. And I can't see my camera. Can you see this, Brenna?
Yep. That little motor on our gearbox, yeah.
Little bitty motor on a gearbox. Probably pretty cheap to produce. Operates on 24 volts. So if we put 12 volts on this thing, do you think it'd spin?
No.
Probably,
Just be
Mhm.
super slow.
but slower. If you put 40 volts on this, do you think it'd spin? Probably really fast. And at some point, once you reach a certain threshold, it would burn the motor up because the windings and the insulation on the windings are not made for that. But imagine this is, let's see, this thing probably won't even give a horsepower because it's so small. But it's designed for very small loads. And part of the reason it has a gearbox is one, to slow the speed down. Because if you put 24 volts on this thing, I bet it spins like an SOB. But you don't want those spiral things in your vending machine going, right? Slows it down, and it helps with the torque. So imagine we wanted 20 horse DC motor. The motor itself would be massive, not a huge deal, but you would need big voltage to run that at the torque you would need it to do the load that you would need it. And big DC voltage is harder to produce, and it's pretty dangerous. The other thing is with DC, the torque on DC motors is not that great. So imagine this thing that I put 24 volts on. I could probably take my hands and put it on there and stop the motor from spinning. Bigger DC motors, you wouldn't be able to do that. That would hurt. But it's harder to control torque with it is. Easy to control speed, harder to control torque.
So like the motor and a screw gun, that's DC as well, right? Because it takes a battery. What's battery means? Those would be DC motors, right?
What?
The motors in like screw gun, power screw gun, the battery operated.
DC, yep.
Because I know those have some pretty good torque too.
Mm-hmm. Yes, but they're also geared way down to handle that torque. And that's the same thing that this thing does, right? If you put this, so let's say we wanted to slow the speed down just by lowering the voltage, right? If you lower the voltage, you lower the torque. So it wouldn't be able to spin your little spiral doohickeys. Synchronous motors used for precise speed control, large slow speed applications, and induction motors are the most common type used in industry. Okay. Voltage is applied to the stator, causing a rotating magnetic field. This is an induction motor, so we're talking about AC. I guess induction can be used in DC too, but let's just assume we're talking about AC motors. Induces a counter EMF. What does that stand for? Electromotive force. Yeah. In the rotor, by the flux capacitor of the magnetic fields, the rotating field is developed in the windings in the rotor, tries to follow, and follow is in quotations because it's not just being pulled along by the magnetic field. There's that whole push-pull thing going on constantly by the three different phases of the motor, or two phases, single phase, same thing, right? You'd have the sine wave is a little different, but there's still the same push-pull going on because of the change in polarity in AC. The rotor cannot spin as fast as the stator because of the load, and the motor slips some. So that motor slip, you understand what that's trying to say?
So would the slip be because the fields can't quite keep up with each other, that every so often the motor kind of has to slack
Yeah,
back,
it's
fall
kind
into
of
place?
correct. It's kind of an inefficiency. So let me see if I can draw this down here if you can see it. But in a motor, you have a rotor, and then outside here where the windings are, you have the stator. And you're producing this magnetic field that's spinning. And it's not, if you had a mechanically driven motor, like if you're using heat or steam or nuclear. So not an electrical motor, but an internal combustion engine, right? You're directly connected by the power takeoff and whatever that motor is to the shaft, to whatever you're spinning. Here, we're working kind of with magic. We're working with electromagnetism. So as the magnetic field is going to constantly spin no matter what. And then the shaft is going to try to follow that. So basically what I'm saying is in the sine wave, if you got 3 of them, every once in a while, your rotor might miss one of these sine waves, right? That's called motor slip. So slip basically is saying that the speed, revolutions per minute of the shaft might be a little slower than the speed of the rotating magnetic field. Not super important, but if you had to have a certain precision of RPM at a lower speed, you'd have to take that into account.
So then you wouldn't want to use an induction, you had to have precision?
No, you still would. You would just have to take it into account. Whether you're using DC or AC or induction or synchronous, that all just depends on the application. But for the purposes of what we're trying to do in this program and what you would most often see in the field is an AC motor. I mean, we're not back there hooking up DC motors on drives, right? We just don't. Bigger motors used to do bigger work. That's what you're going to see most often in the field. Like with your project and those little 24-volt motors, those are specifically designed for that application at that voltage, and you don't really have to worry about that much. When you're talking about doing bigger work, then you have to take into account things like current draw and full load torque and all these things, because when you start a motor up, and we'll talk about this, what happens to your current when you first start a motor? It goes whoop, skyrockets, and then as it gets to speed, it levels out. Starting current. That's the reason that we use drives.
That's like in the car, when you crank it, right?
Cranking amps?
When you first crank your car, the current spikes, right?
Well, I'm sure it does. I don't know enough about it to like see it on a graph or anything, but think about the amount of force it takes to start a motor, right? You're fighting the piston, creating compression and all that. So it takes a huge amount of current to start a car. And that's why they have these cranking amps. Yeah, that's why you can't start. I mean, you've seen a small 12-volt battery, haven't you? They make them pretty small if you want them that small. But that doesn't have the ass to turn over a motor, right? So they make the same voltage battery that's bigger and has more capability to produce that high current that it takes to start a motor. So I think we just talked about this. Different designs and different motors based on different applications. This isn't super important, but there's something called the National Electrical Manufacturers Association, NEMA standards. We've heard about that in Electech 150, right? Good old NEMA. May or may not know this, but it's probably something that you will want to know forever. That's how many watts is in 1 horsepower?
15?
Did you say 15?
Yeah.
Nope.
60.
Nope. It is in your uglies book, but you should probably know this off the top of your head for the rest of your life. Clinchy around? Clinchy would know.
Oh, Clinchy's playing video games. He's no help.
Okay. 746 watts and 1 horsepower. Why? You're a little bit off. Why do you think that's important though?
As far as how much voltage and current you're going to it. So-
Yeah. And sizing wire, right? Going to a motor. So if I have a 3 horsepower motor, and you're going to assume that it's going to be running near full load at a constant, consistently, we can take that amount of wattage and size the wires. Like P equals I times E, right? So if I'm running at full load, let's say it's 3 horsepower motor. How many watts is that? Let's say it's 480 volt. No, let's say it's 208. 208, 3-phase motor, 3 horsepower. And let's say we're pushing that thing to the max. 3 horsepower. So 746 watts times 3.
2,300.
2200 watts at 208 volt. How many amps is that?
So you gotta take 208 divided by, no. The wattage, then the 208.
Be about 11.
Remember this formula?
Yeah,
P equals I times E.
but we got voltage in watt, so it would be,
I equals P over E.
no, so it'd be voltage over watt, right?
So around 11 amps.
Now, is there a math to figure out wire gauge, or is this something you should know? 'Cause I haven't taken
Math to figure out wire gauge.
Yeah, because I haven't taken residential yet.
Oh, you haven't?
No,
No, it's basically a chart.
I mean, doing basic stuff at home, I know that when you got 120, you want 12 days solid. I used to it.
It all depends on what you're protecting it with.
Right.
Doesn't matter what you're using, matters what you're protecting the wire. Like your breakers or your fuses, whatever's protecting the wire. That's how you determine wire size. Well, let me that's not right. If I'm going to be running 15 amps worth of lighting, do I want to put it on a 15 amp breaker? No.
Or a bigger breaker than what you use, right?
Well, off the top of my head, and hopefully those of you who took 111 would know this, but what wire size is good for 15 amps? It's number 14. So if I'm going to run number 14 wire, solid or stranded, doesn't matter, 14 gauge wire is good, can handle 15 amps worth of current without starting to break the insulation down because of heat. Bigger wire can handle more current. So if I had 15 amps worth of lighting, would I want to put 14 gauge wire on it?
Yeah. So you have.
No, because you just need
Can.
wiring for the switch.
But you think it's going to run right at number one? You're not supposed to, I think it's 80%. You're not supposed to load, you're not supposed to have a constant load of more than 80% of what you're,
So you need a 12.
right? So 20 amp. So you always want to err on the side of caution and oversize your wire, right?
Because that's what I use when I run the wires and lights. I use 12. I buy the 12 2 or 12 3.
You don't have to. If your load's going to be 5 amps, I'd go with 14 because it's easier to work with and it's cheaper, right? Yeah. Most lighting circuits are not going to run at 15 amps, but I was just using that as an example. Anyway.
Why is it in most houses? Because I've done a little repair work and I see the 12 gauge everywhere, 12 2.
Yeah, and there's nothing wrong with that as long as there's a 20 amp breaker on it. If you put a 15 amp breaker on it, then that's not a problem because it's just going to trip when it gets to 15 amps, right? If I run a microwave on that same circuit and it goes over 15 amps, it's going to trip. But 20 gauge wire, no, 12 gauge wire can handle 20 amps. So you don't want that. The reverse, though, is the problem. If you put 14 gauge wire on a 20 amp breaker and you run it at 19 amps consistently, you're going to break down the insulation of the wire, right? Because it's too small to handle that much load. So there's nothing wrong with running 12 gauge wire as long as it's on a 20 amp breaker. If it's on a 30 amp breaker, then you're in bad shape. Mm-hmm. Mm-hmm.
I've seen 10, and I've seen 8 like on the 220s.
It all comes down on what you're trying to use, right? What your load is. That's okay. It's good to have these conversations. It all comes down to what your load is, right? Figure out what your load is, what wire you need to take to it to handle that much load, and what overcurrent device you're going to use to protect that wire, right? You kind of start with the load and then work your way back. So along those same lines, that's why knowing how many watt is in 1 horsepower. Yep. I'll post this online too, just so you can review for the quiz if you're not taking notes. 1 horsepower is 746 watts or 2,545 BTUs per hour. Most motors have an efficiency range of 50% to 96%. And energy loss.
I know that term BTU, they use those for burners, don't they?
Batteries.
Could be a BTU burners.
Something thermal unit.
British thermal units.
British thermal unit.
If we use those for burners when I was in the military, we had to fill in the BTU burners.
Burgers?
Burgers.
I know, but it's like what I heard the first time, and I was like, burgers?
Yeah, so that's when we use the burners for, we had to use those to cook the food when we were out in the field.
Okay.
I mean, familiar with BTU.
So energy loss in a motor comes in the form of what? Energy loss in a motor comes in the form of what? What? Okay. Good. You taking notes on your phone?
Google Docs.
Oh.
It was 2,400 something BTU.
2545.
I don't do it.
All right. Horsepower is a measure of how fast work is being done. Horsepower is the amount of work being done over a given amount of time. Work is force times distance. So try to keep all these straight. The work it takes to perform a task is measured in the terms of the force exerted to move something and the distance it is moved. Yep. I'm going to try to write these down because we're going to need them later. We won't get all the way through this PowerPoint today, just so you know. Okay, so horsepower equals work over a given amount of time. Work is a force times a distance. Got it? Good. What is the work required to lift a 300-pound weight from the ground to a 5-foot high platform? How do you know? So work is force times distance. Pound. Your force here is 300 pounds. Your distance is 5 feet. So work equals 300 times 5, which equals 1,500 foot-pounds. Make sense?
Yep.
Hmm?
This is equal to 5 feet.
Mm-hmm.
Is this just a, I'm really taking notes.
That's fine. I'm glad you are.
Equally, it's gonna be 15,000 foot pound. Or 15 foot pound. I'm done.
Okay. Okay. Powerful motor can turn faster or exert more force than a small motor. That's kind of common sense. But in relation to time, motor can do a job in 10 minutes is half as powerful as a motor that can do the same job in 5 minutes. How many foot-pounds of work in 1 minute is 1 horsepower?
33,000 foot pound.
How many foot-pounds of work in 1 minute is horsepower?
33,000.
Point taken?
Did we establish 33,000 or 3,300?
33,000.
No, he's writing it as a.
We're missing a 0.
Why are you yelling at me?
Come on.
It's hard to write with this thing. So in 1 minute, 1 horsepower will do 33,000 foot-pounds in 60 seconds. So how many foot-pounds of work each second would that be?
So you take 32,000 divided by 60. I don't have my calculator.
550.
550 foot-pounds of work each second. It's a lot. Think about it, 1-horse motor is not that big. It's doing 500 foot-pounds of work each second. So that means a 1-horse motor could lift 550 pounds in 1 foot in 1 second. So using the example from above, if you wanted to lift a 300-pound weight up to a 5-foot platform in 1 second, how many foot-pounds per second would that take? We're looking for foot-pounds per second.
You do
So we have 5 feet.
3,300 divided by, or 33,000 divided by 1,500.
Well, just look at this formula. This is what we're looking for, right? Foot-pounds per second. We got 5 feet, 300 pounds in 1 second. Right?
Yep.
Using a 100, hang on, let me erase this. Using a 1-horsepower motor, how many seconds would it take to lift the weight?
No, because the 1-horsepower motor, so it's 550 foot-pounds a second, right?
Right.
So then we'd need to take 1,500 and divide that by 550.
2.72. Roughly. Two and two.
Yep, you're all right. Let's just write it out. So it's 3,300 foot-pounds per minute. This is 1 horsepower. It also equals how many foot-pounds per second? We came up with that?
Yeah, 550.
550 foot-pounds per second. So in 1 horsepower, in this example, we're doing 1,500 foot-pounds of work, right? Per second. So using a 1 horsepower motor, how many seconds would it take to lift the weight?
Okay, 246. 2.72.
Yes, but how'd you know to divide it?
Because, so you're trying to do it by each second, so trying to figure out how many times would 550 fit in the 1,500.
It's a good way to think about it. If I write all this out though, 1,500 foot-pounds per second. Oh, 1,500 foot-pounds of work. So I'm not even gonna write the second part down. And 1 horsepower is 550 foot-pounds per second. No, my writing is not that great. And Ben is right, but we're trying to eliminate everything in the units except for seconds, right? So if we divide 1,500 foot-pounds by 550 foot-pounds per second, It's the same as saying 1,500 foot-pounds times. Yeah. Do you want me to write it out, or do you see how they cancel? I'll write it out. This whole thing is the same as saying times 1 over 550
I got a question. This is
foot-pounds. Hang
When
on.
you do a foot-pound,
Hang on.
is-
In 1 second, right? So if we take this and divide it by that, it's the same as saying this. You see how that is? The reciprocal. In this case, 1,500 divided by 550, these cancel, and what you're left with is about 2.7 seconds. Make sense? And what's your question, Justin?
like, this might be a stupid question, I don't know. But when you're doing the foot-pound, are you drawing the foot? Because it kind of looks
When
like
I
a foot.
write it, when I write it out,
Look at all your foot-pound, like, is that foot LB?
That's- that's
Or-
FT.
No, I know the FT, the LB, is that an LB or is that a foot? you draw?
I'm writing foot
I see that.
pounds, LB.
Okay, because some of those look like you were drawing feet. I don't know.
I'm drawing a foot.
So
Oh,
look at
like this is somebody's feet.
You're drawing a pair of shoes there, buddy.
So look under the 2.7, right? Look next to the 550. Does that not look like a foot? Because that's how I thought you were drawing feet.
This here?
Yeah.
No, it's I'm writing foot pounds per second.
Okay.
FT times LB divided by SEC.
Then they just kind of look like a foot from here. I thought you were drawing feet. I didn't understand that.
Although that foot pounds at the top, there definitely looks like there's a penis there.
Yeah, get your mind out of the gutter.
I didn't draw a penis, you did.
So 1 horsepower motor would take 2.7 seconds to perform that work. So question, an elevator is used to move 20 passengers every minute from the first floor of a department store to the second. Second floor is located 25 feet above the first floor. Maybe I should take the answer out of there. It's all right. We'll work through it anyway. An elevator is used to move 20 passengers every minute from the first floor of a department store to the second. The second floor is located 25 feet above the first floor. The average passenger's mass, that's not mass, but weight, is 175 pounds. These are some small people. Determine the horsepower requirement of the elevator in order to move this number of passengers in this amount of time. What do you think our first step is? Well, even though it's laid out right there, we got to figure out what total weight is, right? So 20 times 175 is 3,500 pounds. And if we're going to move 3,500 pounds, 20 feet, we're going to find the work. Force times distance is 87,500 foot-pounds. And how many seconds did it ask us to do?
1 minute.
1 minute?
Yeah.
If we need to do that in 1 minute, since we're using minute instead of seconds, we're going to use 33,000. So if we're going to do that amount of work in 60 seconds, we need 2.65 horsepower to do that.
So the less passengers you have, the faster this thing's gonna move. Or is there a program, like when you do an elevator, is there a program that's gonna,
All we're saying here is that
I see what you're saying.
if you had less weight, it would require less horsepower to do it in that amount of time. Right? Oh my gosh, my head hurts.
I was gonna say, one floor in a minute is kind of slow for an elevator.
Yeah, well, what if we wanted to do that in 1 second?
Woo!
We could figure that out, right?
Yeah.
So you could just take the 87.
So we
You could divide it by
550.
550.
And what do you get there?
159 horse.
That's a big motor.
Vroom vroom.
All right, so the horsepower that a motor produces depends on 2 factors: how fast the shaft turns and how much force it exerts on the work or the load. Shaft speed is measured how?
You said shaft speed is measured what?
How do you think shaft speed is measured? What's the unit?
RPMs.
RPM, revolutions per minute. And most electric motors in industry run between 500 and 3,600 RPM. Many electric motors are connected to equipment that moves in a straight line, like a winch or a conveyor, crane. I guess some of them move in a rotation. But that presents a problem when we're talking about RPM. Because if we're using a motor shaft, which is round, and we're talking about horsepower, moving something in a straight line, there's something that we have to take into account there, right? A,
Circumference.
circumference. For example, motor shaft, conveyor. We're moving an object X amount of feet. Say this is 5 feet. Now this thing running at, let's say, to make it easy, 3,000 RPMs. How many revolutions would it take to move that thing 5 feet? You have to know what this circumference is. In other words, if I have a circle, what is the distance of this red line? So if I take a tape measure, my awesome drawing of a tape measure, it's a 25 footer, and I wrap this thing around the shaft, what would it measure? That's circumference.
I heard some people say it's like an inaccurate way to measure it. Like you have to, like, some people say like you have to basically base it off of if you were to wrap the whole, like you stretch out the circle into just a straight line. Is it like the same principle or is it?
Yeah, it is. But taking a steel tape measure is going to have all sorts of imperfections, right? You can't, they make nylon tape that you, anyway, the easier way to do it would be to measure the diameter and use pi, 3.14. The larger the drum or the pulley, the faster the equipment will move, right? This goes for gears too. If I have one thing spinning at a certain rate and I expand the size of the shaft, it's going to move that conveyor faster, right? Because there's a bigger circumference. All right, last slide for today. Force that the motor produces depends on the torque exerted by its shaft. Can anybody describe to me what torque means? Torque.
Power it takes to turn, is a force.
Force. Torque is a force. It's a rotational
It's
force.
not a force you're getting for,
Yeah, that's a good way to put it too. But just remember that torque itself is a force. It's a rotational force or a twisting force. Torque is the twisting force produced by the magnetic attraction and repulsion inside the motor. So you have the magnetic field spinning, the magnets pulling on the shaft, and you have a rotational force. That's what actually is doing the work of the shaft. Torque is measured in both pounds of straight line force and the distance between the center of the shaft and where that force is measured. A motor which is producing a certain force at a small distance will need to exert more torque to produce the same force at a larger distance. So that bullet point there, think of it in terms of this. I have a 50-pound bag. Can you see me, Brenna?
I see you now.
I have a 50-pound bag of pretzels. This looks like it's 50 pounds, right?
give or take.
I'm not a small guy, so if this really was 50 pounds, I could lift it straight in the air right here, right? But if I hold this thing all the way out, it's going to take a lot more torque or rotational force here to lift that thing up in the air. If this was 50 pounds, I probably wouldn't be able to do this.
I'd throw your shoulder.
Yeah, that's what torque means. So it has to do with the distance between here, which is the center of the shaft, my shoulder, and where that load is. So keep that in mind. We're going to pause there today. Wednesday, we'll review this slide and then move on in the PowerPoint. But to reiterate something on this slide, what is the twisting force produced by the magnetic attraction repulsion inside the motor?
What is torque?
Torque. And this is me dropping the mic. Means
Boom.
one for today. Cool?